Welcome to Power Electronics Education, Electronic Book, Lecture 2, Power Switches. This lecture is presented by Dr. Firuz Zare. The contents of this lecture are ideal and practical switches, losses, harmonics and EMI, types of switches, gate drives, power switches in different applications. So key elements in a power converter are power switches, which operate at high voltage and or current. They chop DC or AC voltage current based on a pulse pattern generated by a controller to achieve a desired voltage or current. That means a controller can measure the output voltage and output current, compare with the reference. So the reference signal can be either current or voltage. So finally, the controller can generate the gate signal, and this signal is applied to power converter, which basically turn on and turn off the power switches. And if we have a DC current or DC voltage, here we can chop the current or voltage based on the pulse pattern generated by the controller. That means we can synthesize any current or voltage waveform, and then we can generate that one in high voltage, high power. So basically power electronic is power processing and is a mapping from low voltage into high voltage system. When we consider power switch as an ideal switch, that means the switch can handle unlimited current and blocks unlimited voltage. So unlimited voltage and unlimited current, and the voltage drop across the switch and leakage current through the switch are zero. So that means when the switch is turned on, the voltage across the switch is zero and the current through the switch is zero when the switch is off. So the switch is turned on and off with no rise and fall times. So that means no rise and fall times. That means the switch is very fast. So this assumption helps us to analyze a power circuit, but for design and practical consideration, we should consider real power switches. In a real case, ideal switches do not exist. During switching transients, there are significant switching losses associated with DVDT and Diode. These phenomena depend on several issues such as characteristics of power switches, control signals, gate drives, stray parameters, and operating points of the system. So suppose that the switch is in turn-off state. So when we apply gate signal just at this stand, then the voltage across the switch is decreasing while the current through the switch is increasing. So here over this switching time, what's happened? The power dissipate in this switch, which equals to voltage times of current, means that this is the switching losses associated with turn on state. Then over this switching time, the voltage across the switch is increasing while the current through the switch is decreasing, and then we have these losses as well associated with turn-off state. So this is switching losses. So over one cycle, over one switching cycle, which is defined as a TSW, so we have one turn on and one turn off losses. And then when the switch is on, because the voltage across the switch, the voltage drop across the switch is not zero, so the voltage times of current defines the conduction losses. So this is conduction losses. But because assuming that the leakage current is zero, so 0 times of voltage means that the conduction loss when the switch is off is 0. So in this case, we can see that by changing the switching time, either during turn on time or turn off time, we may decrease the switching losses, but the point is that we can increase the DVDT and the IDT. These are main issues in power electronics because create significant overcurrent and overvoltage and create significant EMI issue. So real power components have limited power, voltage, and current handling capabilities. They have also limited switching speed, and that's because of charging and discharging internal capacitors exist between the junctions, which limit the maximum operating frequency and create switching losses. Also, we have to notice that on-state and on-off state resistance or voltage drop and leakage current create conduction losses. So when we design a power electronic circuit, we have to notice that we have to calculate the total loss associated with switching and conduction losses. Three major issues to design a power electronic systems are losses, harmonics, and EMI or electromagnetic interferences. These issues affect system cost, size, efficiency, and quality, and is a trade-off between these factors. It's very important to know these issues at the earliest stage of a design and select appropriate power switches. So let's start with losses. There are different types of losses in a power converter, such as conduction loss and switching loss, which happens in power switch when the switch is getting on and off when the switch is in on state. Losses in a controller, because controller consists of microcontroller, op-amps, and comparator. They consumes power. And losses due to charging and discharging stray inductances, and in some applications when we have a planar busbar or significant stray capacitance, they can create also losses. So when a switch is turned on or off, energy is lost during the switching transients when operating points of the switch are changed from on to off state to active state. So that means, suppose that the switch is off and now we apply gate signal, and then the switch is getting on over this switching time. So at this point the switch is in on state, so this is the voltage drop across the switch. So the point is that because power, as I mentioned before, equals to voltage times of current, so that's why this is the switching losses when the switch is getting on. And we know that when the switch is off, normally leakage current through the switch is zero, so that's why we don't consider conduction loss when the switch is off. But because the voltage across the switch is not zero, depends on the switch, but the forward voltage is not negligible, so voltage times of this current creates this conduction loss that we will consider in the total loss when we consider the conduction loss. So same scenario happens when the switch is getting off. That means over this cycle the voltage across the switch is increasing, the current through the switch is decreasing. So this is the switching loss when the switch is getting off. So finally these are the total switching losses, and this is the conduction loss, and finally we can define the total loss, which consists of switching loss and conduction loss. So the average power loss in a switch over one switching cycle, which is defined as a TSW, is given by the following equation. So this is the total loss, average loss over one switching cycle. So basically we can calculate based on this equation. This is the current through the switch, this is the voltage across the switch. So then finally we can define as a conduction loss and switching loss. So assuming that the on and off switching time are small compared to switching cycles, so that means in this case also assuming that the leakage current through the switch is zero, so we can easily find the conduction loss. So conduction loss is voltage drop across the switch times of current through the switch. Suppose that over one switching cycle current is constant, and times of this ratio. This ratio means that turn on time over switching cycle, which is basically defined as a duty cycle. So finally we can simplify this equation, and the conduction loss, average conduction loss over one cycle, is the voltage drop across the switch times of current through the switch and times of duty cycle, means the turn on over switching cycle. We can calculate the switching loss based on instantaneous current and voltage waveforms. Normally we approximate the current and voltage waveforms to be able to find the switching losses, but in real case it's quite difficult and challenging because we need high bandwidth measurement circuits with low stray inductance to be able to measure the voltage and current waveforms accurately. So let's look at the switching losses. Basically, switching losses over one switching cycle is given based on this equation. That means this is the switching loss associated with the time that the switch is getting on, and this is the switching loss when the switch is getting off. And T1 is the time that we apply gate signal, and TSW on is the switching time when the switch is getting on, and here T2 is the time that we remove the gate signal, and TSW off is the switching time when the switch is getting off. We can show that the switching loss is proportional to the switching frequency. That means based on this simple equation, which shows that the switching frequency equals to 1 over switching cycle, then we can put in the previous equation, and the switching loss equals to switching frequency times of switching losses associated with on and off time. So in this case we can see that by increasing the switching frequency, the switching loss is increased, but we know that by increasing the switching frequency we can improve the quality, we can reduce the harmonics and ripple. In all power electronic systems there are stray inductances and capacitances due to interconnection between the power components via wire, conductor plates, and or any other types of conductors. In a power electronic circuit, when we turn on and off a switch, we may charge and discharge a stray inductance associated with the current loop as shown in the following figure. That means suppose that this current loop has this stray inductance. So once we turn on the switch, we have this current through the inductor. So that means suppose that the current is given this equation. So we store energy in this inductor, and once we switch off, that means the current through the inductor, these amperes, that means we actually lose this power. The second issue is that once we switch off, if this is the current through the inductor, then we decrease it down to 0. So this is basically, if this is the current, so basically this is significant the IDT, and this times of a stray inductance gives over voltage, and that over voltage appears across the switch and it may damage the switch. So that's why, because of two issues, extra losses and also over voltage, we should reduce the stray inductance. Same scenario happens when we have a stray capacitance. That means when the switch is off, we charge the stray capacitance, which may appear across the switch, or if you have a plate, copper plate. So parallel copper plates means that we create stray capacitance. So once we charge this capacitor, that means we provide voltage across the switch, and that means the energy stored in the capacitor associated with this equation. and that's the voltage across the capacitor. So what's happened when we turn on the switch, in this case we discharge the current through the switch. There are two issues. Again, we lose this energy. That means over one cycle, if we have turn on and turn off every time we charge and discharge the capacitor. The second is that when we turn on and turn off, that will be the voltage waveform. So that means we have different DVDT here times of stray capacitance gives current. So the current depends on DVDT and stray capacitance. So if this stray capacitance is significant, then we have a significant current through the switch which may damage the switch. Finally, the average power loss due to these stray components over one switching cycle is given by this equation. So this is the average power loss if we have multi current loops. So we have these losses due to stray inductances and stray capacitance. So instead of 1 over switching cycle, we can write switching frequency, because this is equal to switching frequency. So that means, again, by increasing the switching frequency, we increase the total loss, but again the advantage is that we can reduce the harmonics. In a power electronic system, there are other circuits such as gate drives, controllers, sensors, and passive filters which consume powers, and also extra losses associated with these components. So when we are talking about filters, that means the capacitors, inductors can consume the power, and that's because they are not ideal components. When we are talking about, for example, sensors, basically different sensors like over voltage, over temperature, over current, and snowball circuit, they may consume power. When we are talking about controller, basically controller consists of logic device, for example microcontroller or A to D or D to A, so they consume power. And also analog circuit like operational amplifier or comparator, they consume power. And when we are talking about gate drives, that means the gate drive, either high side gate drive, low side gate drive, or the other logic device to control the dead time, they consume power. So in this case, we consider extra power as P other, which is associated with these losses. So when we calculate the total loss in a power electronic system, so we should consider this loss as well. Welcome to Power Electronics Education Electronic Book, Lecture 2, Power Switches. This lecture is presented by Dr. Firuz Zare. The total losses in a power electronic system are given by this equation. That means if you have n switches, the switching loss in the first switch is given by this equation, which is basically consists of conduction loss plus switching loss, and same for the second switch or the rest of switches. Plus we consider the extra loss associated with stray components, and also another loss because of other components like microcontroller, filter, and so on. So this is the total loss in a power electronic circuit, which can help us to find the efficiency of the system. Now we can find an efficiency of a system based on input and output power, and also based on the total losses. So basically, if this is input power coming to the system, and if this is the total losses in a power electronic system, so then this is the output power, which is given by this equation. And then we can say that efficiency is output power over input power. So instead of output power, we can write this equation and put it here, and we can simplify into this equation because P in over P in is 1 and P loss over P in is written here. So finally we can say that if we have no losses, if the system is lossless, then this portion, this part is 0, and then we have maximum efficiency. And this graph shows that when losses is increased, actually the efficiency is decreased. So it's quite important to understand the total losses and how to optimize and reduce in order to improve the efficiency of a power electronic system. In a power converter, high losses increase the junction temperature of power switches, which may damage them if heat is not transferred to ambient. So it may need a heat sink to transfer heat from junction into ambient, which increase the cost, size, weight of the power converter. So basically what's happened here, when we have high losses, that means we have high temperature. So basically junction temperature, if it's very high, then we may need heat sink to transfer the heat from junction into ambient. So in this case, this component increase the cost, size and weight of the power converter. So if we can reduce the losses, if we have high efficiency system, then we can also reduce the size of system and also reduce the cost of the whole power electronic circuit. Now let's look at harmonics. In power processing, an input voltage or current is chopped based on a pulse pattern which generates a desired output voltage and or current waveform. This process generates harmonic contents on the output waveform and or inject high frequency current into the input voltage source. Switching frequency and passive filters have a significant role in reducing the harmonic magnitude on both sides, and we can classify them as load side. That means if the output voltage is DC, then we should consider the ripple magnitude. The second case, if the output voltage is AC on the load side, we should consider the harmonic contents and THD or total harmonic distortion. And if the input source is AC, then we should consider the THD and power factor. For example, in this case, if we have an AC to DC converter, because of input current may be distorted by the load, then in this case we inject significant harmonics into the system. So that's why we should consider the input current, and we have to reduce input current based on IEC standard. In order to see the effects of the switching frequency on output voltage, we can see these two voltage waveforms. For example, in this case, the switching frequency is FSW1, and this switching cycle is greater than this switching cycle. That means FSW1 is less than FSW2. So this voltage waveform, current waveform, or this circuit has higher switching frequency than this circuit. So in this case, let's look at the output ripple. For example, if we define this ripple on output current, so we can define this one as 2 delta I1, and here we can see that the ripple is much less than the other waveform. So if this is 2 delta I2, then here we can see that by increasing the switching frequency, we increase the switching losses but improve the quality. So this is quite important to understand the effects of these issues. For example, you can see that by increasing the switching frequency, so we increase the losses but improve the harmonics, and also in some applications, especially DC-DC converters, when we increase the switching frequency at the range of 50 or 60 kilohertz, then we may also affect the EMI. And the other case is that changing the switching time, we may change the losses, but we may also increase the EMI. So it's quite important to understand these three factors and how we can control and we can optimize our design. So in the previous slide, we have found when the output voltage is DC, how the switching frequency can affect the output ripple and also losses. Now let's consider in this slide if the output voltage is AC, so how we can control the harmonics and THD. So look at this current waveform and this current waveform. So here you can see that the ripple is significant compared to this current waveform. So here it looks like that we get almost a sine wave, but here we have sine wave plus harmonics. So a drawback is that this one has a high switching frequency compared to this circuit. So the point is that by increasing the switching frequency, we can reduce the harmonics and also reduce the total harmonic distortion, but the drawback is that we may increase the switching losses. Now let's look at the input current waveforms in an AC-DC converter when the AC is the grid and also the output is connected to a capacitor and resistor. For example, if we have a diode rectifier as AC-DC converter, so if the output is connected to a capacitor and resistor, because capacitor can operate as a filter and provides better voltage for this resistive load, but the point is that the input is connected to a grid voltage. So now we can look at the current waveform. So basically here you can see that the current waveform input current is not a sine wave. That means this current has significant harmonics. The reason is that over this time we charge the capacitor up to this peak value and then discharge it again. So that's why the current waveform is not sine wave. Another possibility is using power factor correction circuit. That means in this case we can shape the input current into a sine wave in phase with the voltage. So the advantage is we can improve the quality. The advantage is we can reduce the harmonics. So when we are talking about harmonics, when the input is AC, so it's quite important to have a better current, because otherwise we are not allowed to inject significant harmonic into the power system. We have considered losses and harmonics. Now let's consider the EMI, electromagnetic interference. So two major sources of EMI in power electronics are DVDT and Diode. So basically when we switch on and switch off, we chop the DC voltage or DC current. That means we have significant Diode and DVDT. So what's happened? Basically, if there is any stray capacitance over this switching time, when the switch is getting on or off, because of significant DVDT and because of stray capacitance in the circuit, so we have a leakage current which equals to stray capacitance times of dVdt. And the same scenario when we switch on and off, so we may have significant Diode, because if we have different current loops, when we switch on and switch off, the current actually is increased and decreased. And if there is any stray inductance associated with different current loops, then we may have overvoltage, and that's because of stray inductance times of significant Diode. So what we can do, the best thing that we can do is to minimize and reduce the stray components, because in this case we can have a better system, we can have a better layout, and we can have a better efficiency. And the point is that there are some constraints on Diode and dVdt. The point is that we cannot decrease or increase these factors easily, because by changing Diode we may change losses, and in some cases we're not allowed to increase losses. So if EMI is a big issue, then we should consider this factor, because this factor depends on the design, how well we can design a layout, which topology we use, and how we can optimize our design by having a better layout and less stray components. For example, here let's look at two different dVdt and Diode. In this circuit, when the switch is off, when we apply gate signal at this time, the voltage across the switch is decreasing. That means the switch is getting on, and the current through the switch is increasing. That means the switch is getting on. So this is dVdt, and this is Diode. And if you look at this area defines the switching losses associated with turn on time, and same scenario happens when the switch is getting off. So by decreasing the switching time, it doesn't matter when the switch is getting on or off. That means we can control the losses. So if you look at this voltage and current waveforms, by decreasing the switching time here, what's happened, we can reduce the losses. But a drawback is that this dVdt is significant compared to this circuit or this voltage waveform. Same happens here. This Diode is significant compared to this current waveform. So again, we can see that is a trade-off between these factors. That means by decreasing or increasing the switching time, we may change the losses. Power switches are the key parts of a power converter, and they are classified based on the switching speed and power handling capabilities, such as maximum blocking voltage and carrying current. In modern power converters, achieving high efficiency is a main concern and a key factor which saves energy in the converter. Achieving a high efficient converter is very challenging, and we need to compromise with other key factors such as quality and power density. It's apparent that increasing the switching time and decreasing the switching frequency decrease the total losses, but main drawbacks are increasing EMI noise and reducing quality of the power converters due to increasing the ripple on the output voltage or current. The main challenge are to have a good understanding of EMI issues in power converters and layout to reduce EMI as low as possible without having extra passive components. And in semiconductor manufacturing, to develop a new generation of semiconductor devices to be able to operate at higher temperature to increase the capabilities of the converter with higher reliability. So what are the design steps? Suppose that we're going to design an AC drive system, AC motor drive system. So in this case, we need a group of engineers, for example, motor design engineers, control and hardware engineers, mechanical engineers, test and measurement group, and finally EMI experts. So what are the key points? As we discussed that losses, harmonics, and EMI are the key factors. So in this case, we should optimize everything. We should reduce all of these issues at the beginning stage of a design. So when they design an electric machine, they should actually find all the capacitive couplings between the windings, stator and rotor. And in this case, if there is a significant capacitive coupling, EMI expert can help to reduce this capacitive coupling, because what we get out of this one at the end, we may have significant EMI. So if we consult and communicate with EMI expert, in this case we can optimize our system, because once we design an electric machine or transformer, and once we actually design a controller and hardware for this design, so it's not easy to reduce the EMI. So in this case, the only solution is to have a better layout and EMI filter. But with communicating with other engineers, especially EMI expert, so what we can do, we can look at the capacitive coupling and see if there is a significant capacitive coupling, we can optimize the design and reduce the capacitive couplings. So the next group are control and hardware engineers. So in this case, they can find a good topology for that design. They can find a good pulse width modulation technique, or define switching frequency and switching speed, and also layout. So if there are some problems, for example, EMI problem or losses, then we can consult with EMI expert. Then whether we can change the PWM technique, or we can change the switching speed, or we can change the switching frequency, and also we can also work on the layout. So in this stage, the rest of engineers, especially mechanical engineers and EMI expert, can see if there is a thermal problem or EMI problem, then we can work at this stage to improve the system. So the next group is mechanical engineers. So in this case, if there is a thermal problem, if there are some problem associated with interconnection, they can look at the system, they may design a heatsink, and if you can't actually improve the losses, or if you can't actually change the switching frequency because of other design issues such as harmonics, then we may need to have a heatsink. And also layout, because of packaging, because of other issues, then we need to consider the layout. And in this case, if there are some problems, especially when we design heatsink, we need also look at the EMI, because there are maybe some capacitive coupling in the system which may affect the system's performance. So in this case, we may communicate with other engineers and see how we can improve the system. So finally, when we finish the design, we need to test and measure the system performance, some other key factors. If there are major problems, we need to change, for example, some of the passive components, especially filter and also layout. So in this case, based on several tests and measurement, we can see some of the problems. If there are main problems, we may need to change some of the control issues or pulse width modulation techniques, or some of the algorithm. And if there are some major issues in the test because of the structure of the system, then we may need to communicate with mechanical engineers to improve the system. Or if there are some EMI problems, then we need to communicate with EMI expert. So we like to improve the system at the beginning of stage, because at this stage we like to have less problem, because in this case that means we already designed the machine, we already designed the controller hardware, we already designed the mechanical system, packaging, everything. So we don't like to have a major problem, because if there is a major problem at this stage, then we need to redesign again. So that's why if we communicate with each other at the beginning stage of a design, we may have less problem at this stage. Welcome to Power Electronics Education Electronic Book, Lecture 2, Power Switches. This lecture is presented by Dr. Firuz Zare. So finally, when we design the AC drive system, then at the last stage we need to design EMI filter. At this stage we like to have less EMI problem. So that means if we consider everything at the beginning stage of a design, that means we can improve the system, and at the last stage we have less problem to reduce EMI noise. So it's quite important to communicate with each other and then to consider these three factors: losses, harmonics, EMI, because these factors are quite important, because some of the factors which can affect are switching losses, switching speed, which create DVDT and Diode, and also stray components such as stray capacitor or stray inductor. So these are quite important when we design, and if we can optimize these factors, these parameters, that means we can optimize the system based on these three factors: losses, harmonics, and EMI. So let's look at these three main factors: losses, harmonics, and EMI, based on these two parameters: switching frequency and also the DVDT and Diode. So what we need basically when we design a power electronic systems, the hardware section is how to define a good switching frequency and how to define a good switching time, which defines DVDT and Diode. Here we can see that changing DVDT and Diode, or changing the switching frequency, may affect losses, and we have found that by increasing losses or changing losses we may change efficiency. More losses means more thermal problem, and in this case we need to have a heatsink which increase the cost, size, and weight of the system, and more temperature means reliability problem, and in this case packaging problem, because we need to design a heatsink. In some applications, if switching time or switching cycle is much longer than transient time, so the effect of DVDT and Diode on harmonic contents is negligible, except at very high switching frequency. So that's why we can see that switching frequency can affect harmonics, can change harmonics. For example, at very high switching frequency we may have less harmonics, but the drawback is more losses. So let's concentrate on switching frequency. So by changing switching frequency we may increase or decrease the harmonics. So in this case the size of passive components is changed. So that means at high switching frequency we need small components as passive components for EMI or line filters. And also we can control and change the ripple on output voltage or current. That means increasing the switching frequency means that we can have less ripple on output voltage or current. And also increasing the switching frequency means that we can decrease the harmonics in output current, and then we can decrease the losses associated with the core losses in inductor or in transformer. But again, we have to consider again here that increasing the switching frequency can increase the losses. So it's not easy to define a switching frequency, or it's not easy to increase the switching frequency if we just concentrate on harmonics, because if you just concentrate on harmonics, we may increase the losses and also other issues. So the last factor is EMI. So basically EMI can be affected by switching frequency and also DVDT or DIDT. So in one application I would like to highlight the problem associated with switching frequency. For example, in switch mode power supply, basically in some applications we like to increase the switching frequency. So if switching frequency is above, for example, 50 kilohertz, so what's happened, the third sideband will be around 150 kilohertz, which basically is in the range of EMI. So that's why in some applications when switching frequency is pretty high, we may have EMI problem because of switching frequency. And in some applications, because of significant capacitive coupling, especially in AC motor drive system, so we may have significant leakage current. And in some applications when we have significant stray inductance, because of the IDT, we may have significant overvoltage. So these are the issues that we need to consider when we design a power electronic system. There are different types of power switches. For example, diode, BGT or power BGT, IGBT, MOSFET, GTO, and Thyristor. We will look at all switches and describe in which topology we can use these power switches. BGT is a current control device which needs a sufficiently large base current to turn on the transistor, and the base current must be supplied continuously to keep it in the on state. So basically the switching losses is significant, and the reason is that the turn off time is very long, and also because of a special gate drive to supply continuous current. So that's why this type of switch is not very common in modern power electronic systems. The next switch is GTO. So this switch is a controllable switch which can block negative voltage as well. It can handle large voltage up to few kilovolts and also large current up to few kiloamps. So this is a good switch. This is a good power switch for power system applications. But the problem is that the maximum switching speed is around 20 up to 30 microsecond. And in this case, because it's a good switch for high power applications, so it's a good candidate for high power motor drive systems, for tractions, and also active and reactive power control used in power system, especially in distributed generations, renewable energy systems. So in modern power electronic systems, these are the important power switches, which is power diode, power MOSFET, IGBT, and also SCR or Thyristor. So what's happened, we normally use SCR in very high voltage, high power applications, especially in power system, or in very low power AC systems, for example, for very simple and cheap AC drive, AC motor drive. So we can concentrate on these four switches: SCR, MOSFET, IGBT is a very good switch for high voltage applications, and diodes for different applications, for example line, rectifier, or converters. Power diodes. A diode is an uncontrolled switch. That means the switch is turned on and off based on its current and voltage. So once the voltage across the diode is getting positive, So in this case, diode actually conducts, and the current through the diode depends on load impedance, because in this case normally diode, for example, look at this simple circuit. If you have a diode which is connected to a resistive load, so in this case, if we have, for example, AC voltage, so once we have positive voltage across the diode, when diode conducts, so basically the voltage across the diode, suppose, is very low or almost zero. So in this case, the input voltage appears across the load. So load impedance, if for example is resistive load, load impedance defines the current through the diode. So when the voltage across the diode is getting negative, so in this case diode blocks, that means in this region the current through the diode is almost zero, or leakage current. So that's why we can see that diode conducts in this quadrant. That means it can conduct positive current when it turns on, and it can block negative voltage when it's off. When a diode is switched off, energy stored between p-n junction must be discharged in order to block the voltage and current. So the electric charge stored between the p-n junction and the time to discharge it are called reverse recovery charge and reverse recovery time, which affect switching speed, losses, and EMI. So basically we can calculate this charge, which is QRR. If you look at this triangle, we can calculate this area, which defines the total charge. So if this is the peak of current, which is called IRR, maximum reverse recovery current. So this area equals to current times of time, which is basically in this triangle this side, divided by 2. And in this case we can calculate the reverse recovery charge. We can classify diodes into Schottky diode, which have low forward voltage and they are very fast. So a main drawback is that they are not available at high voltage, so they cannot block high voltage. So the next type is fast recovery diodes, which are used in most modern power converters, especially in inverters, and they can handle few kilovolts. And the next type is line frequency diodes, which can block high voltage up to several kilovolts and handle current up to several kiloamps, but reverse recovery time is long compared to other types of diodes, and there are suitable power diodes for operating at 50-60 Hertz, for example operating at line frequency, especially in AC, DC rectifiers. SCR, or silicon control rectifier, or Thyristor. This is a special power switch which was very common in the past, but at the moment in modern power electronics we normally use these type of switches at very high voltage applications or very high current applications, because they can handle high voltage and deliver high current. So basically we can use them in HVDC system, high voltage DC system, or we can use them in low power AC/AC converters, in which a simple and cheap converter is required. So a thyristor basically operates when we apply gate signal. A thyristor can be turned on, but we cannot turn off the switch by applying gate signal. So this is a special switch. That means turn on is controlled, but turn off depends on the thyristor current and also the voltage across the thyristor. Suppose that the input voltage is an AC type, and how we can turn on a thyristor in this simple circuit. So basically, over first half a cycle, because the input voltage is positive, then the current through the resistor is 0. So in this case, the voltage across the thyristor is positive. So now we can apply gate signal. So by applying gate signal, then we can turn on the thyristor. So once we turn on the thyristor, that means the current through the thyristor depends on this resistor. And at the end of this cycle, first half a cycle, because the voltage actually goes to 0, so that means current through the thyristor is 0. So in this case, the thyristor is getting off. So in this case, thyristor cannot operate in the second half a cycle. Let's look at current voltage characteristic of a thyristor. So basically, thyristor can block negative voltage, and also it can block positive voltage. That means if we don't apply gate signal, so it can stand at that positive voltage. But once we apply gate signal, the thyristor actually turns on. So we call latching current, which is defined by IL, and also holding current. Latching current means that when the thyristor is getting on, the current through the thyristor, when we remove the gate signal, should be more than latching current. So if the current through the thyristor is less than that one, then the thyristor is getting off. And in any case, in any circumstances, when the system is operating, when thyristor is conducting, then if the current through the thyristor is getting less than holding current, so thyristor is getting off. How to turn off a thyristor? Basically, to turn off a thyristor, we have to notice that the thyristor is not a full control switch. That means we can turn on a thyristor by applying gate signal, but we cannot turn off a thyristor by removing the gate signal. So there are two methods that we can turn off a thyristor. One is using auxiliary device, auxiliary circuit. That means, for example, providing negative voltage across the thyristor and also bypassing the current through this auxiliary circuit. So in this case, the current through the thyristor is decreased, and once the current through the thyristor is getting less than holding current, then thyristor will be off. But we have to also notice that because there are PN junctions, we have to consider reverse recovery time. That means the charge between the PN junctions must be discharged, the electric charge must be discharged. Otherwise, if we apply positive voltage, we may turn on the thyristor again. The other point is that in some AC-DC converters, because the line voltage is AC, and if we use thyristors, so the point is that because the line voltage is getting negative in the second half a cycle here, then the current through the thyristor may be decreased, especially when we have resistive load or inductive resistive load. So this is another way, natural commutation. That means that the current through the thyristor can be decreased and the thyristor can be turned off. When we design a power electronic circuit with thyristors, we have to control the voltage stress across the thyristor. That means we have to control DVDT. Because the thyristor is a 4-layer device, we can consider that one as 2 transistors in this configuration. The first transistor is PNP transistor. So if we split these junctions, these layers, then this corresponds to PNP transistor, and this NPN correspond to this transistor. So here we have base emitter in this BGT, that means base emitter, and here we have emitter base, which is basically this junction. So when we have positive voltage across the thyristor, then if we have significant DVDT, which happens because of any other switching, because of any transient, and if this transient happens across the switch, across the thyristor, because of this stray capacitance exists between N and P, which means this capacitor. So basically in this configuration, when we look at anode and cathode, because of this voltage drop, which is negligible, this voltage drop, which is negligible, so if we have significant DVDT because of this capacitive coupling, we may have significant leakage current, and this leakage current can be defined as a gate current, which may turn on the thyristor. So that's why when we have a power electronic circuit, and if there is, for example, a thyristor in this circuit, so we have to be sure that by turning on and turning off the other devices in this power converter, the voltage across the thyristor has less stress. Otherwise, as I mentioned before here, we may have significant leakage current, and that significant leakage current can turn on the thyristor. There are different types of thyristors. Phase control thyristor is a good switch to operate at very high power, very high current, and very high voltage. So that's why we can use this type of thyristor in power system applications. The next type of switch is light activated thyristors, which can be used in high voltage applications as well, because we have galvanic isolation and we don't need to have a special gate drive when they operate in high voltage. And the next one is low voltage, low power thyristors for light intensity control or dimmer, or any other AC converter operating at line frequency, suitable for cheap AC motor drives. Let's concentrate on control switches. MOSFET is a control switch. That means we can turn on the switch by applying gate signal and is voltage control, and when we remove the gate signal, the MOSFET is getting off. So MOSFET is a very fast switch, and turn on and turn off time are very short. It can be around 100 nanoseconds. And the point is that when a MOSFET is getting on, the conduction loss depends on turn on resistor. So that's why at high voltage this resistor is getting high, so it's not a suitable switch for very high voltage application because the total loss will be high. Welcome to Power Electronics Education Electronic Book, Lecture 2, Power Switches. This lecture is presented by Dr. Firuz Zare. When we design a power electronic circuit based on MOSFET, we have to look at the datasheet, and if there is any body diode, then we have to consider that one, because body diodes are not very fast diodes. So that's why in order to block that one and use MOSFET in high frequency applications, so we need to have fast diodes in this configuration. That means this fast diode can block the body diode. So that means if there is positive current can pass through this diode and MOSFET. And if we have to operate in this quadrant, that means blocking positive voltage and conducting negative current, then this fast diode can conduct negative current. So in this case, we can use this type of MOSFET with two diodes, fast diodes in this configuration, which gives these operating points operating in this quadrant, blocking positive voltage, conducting positive current, or blocking positive voltage and conducting negative current. The next control switch is IGBT, or insulated gate bipolar transistor. Basically, it's also voltage control. That means by applying gate signal, we can turn on the IGBT, and when we remove the gate signal, the IGBT is turned off. So IGBTs are fast switches with high voltage and current capabilities. In most of modern power electronic systems, we can use IGBTs. So turn on and off process is similar to MOSFET, and they are very fast. They can operate at high voltage, for example around 2-3 kilovolts, and operating at high current, for example 1200 amps, and the voltage drop across the switch when the switch is in on state is between 2-3 volts. When we design a power converter, it's quite important to understand directions of power flow, which define what type of switches we need to handle that power flow. As most of loads are resistive inductive, so a switch should handle bidirectional current, and sometimes they have to block positive and or negative voltage. So for these applications, we need to combine some switches in parallel and or in series in order to have a flexible switch to operate in different quadrants. For example, if we have to provide positive voltage and positive current, that means operating in this quadrant, or if we have to operate in this quadrant, means providing positive current and blocking negative voltage, or if a switch has to operate in both quadrants, that means providing positive current and blocking positive and negative voltage. So in this case, we need to have a special switch to be able to operate in this quadrant. So same happens for this quadrant and this quadrant. So that means sometimes a switch can operate only in one quadrant, or two quadrants, or even four quadrants. So in this case, we need to have a flexible switch to be able to handle this power flow. Let's look at bidirectional switch. That means a switch can handle positive current and negative current, and also can block positive voltage. So basically, if you have a control switch like IGBT with an anti-parallel diode, it can handle positive and negative current and block positive voltage. For example, if we combine this IGBT or transistor with anti-parallel diode, so what's happened? When there is no gate signal, this transistor can block positive voltage, and this diode can block positive voltage. When we apply gate signal, this transistor can conduct positive current, and if the load current is negative, this diode can conduct negative current. So that means this combination can be defined as a switch, which is control switch, and it can operate in two quadrants. That means conducting positive and negative currents and blocking positive voltage. Bipolar switch. A control switch like an IGBT in series with a fast diode can operate in these quadrants. That means it can block positive voltage and negative voltage and it can conduct positive current. For example, if the voltage across the diode and across the switch is positive, that means the switch can block positive voltage if there is not any gate signal, and if the voltage across the switch is negative, that means this diode can block negative voltage. And if the current through the switch is positive, that means the switch can handle positive current when we apply gate signal. So basically a combination of this diode with this IGBT or MOSFET can be defined as a switch which can operate in these two quadrants. Bidirectional and bipolar switch. In some applications, power switches should have bidirectional and bipolar capabilities. Three different combinations shown in these figures. That means if we have to operate in four quadrants, blocking positive voltage and negative voltage, conducting positive current and negative current. So let's start with this configuration. We can have two diodes and two switches. In this configuration, if the current is positive, it can pass through this leg. When we apply gate signal, then this switch can conduct. If the current is negative, this diode can conduct, pass through the switch when we apply gate signal to this transistor. So in this case, this type of configuration can operate and can handle positive and negative currents. Now, if we have positive voltage, here we can see that in this leg, this transistor can block positive voltage, and in this leg, when we have a positive voltage, this diode can block positive voltage. And if we have negative voltage, that means this polarity. In this case, this diode can block negative voltage, and in this case, this transistor can block negative voltage. So that means this configuration can also handle positive and negative voltage. Now let's consider on this configuration, again two diodes and two switches. When we have positive current, in this case, the current can pass through this switch and through this diode. And if we have negative current, can pass through this switch and this diode. That means again, this combination can handle positive current, negative current, and when we have positive voltage across the switch, then in this leg, one of the diode can block, for example this one, and in this case, this switch can block. When we have negative voltage, again, one of the diode can block in this configuration, in this leg, and one of the switch can block. So in this case, again, this configuration can block positive and negative voltage. Now let's concentrate on this configuration. That means if the current is positive, the current can pass through this diode, and when we apply gate signal, then this transistor can operate. So this is the current loop. And when the current is negative, that means this diode can conduct, and when we apply gate signal, this transistor can operate, and this is the current loop. That means this type of configuration shows that the switch can handle positive current and negative current. And what's happened if we have positive voltage across the switch? So in this case, if we look at this leg, one of the diode can block, and if we look at this leg, one of the diode can block. And when we have negative voltage, again, in these legs, this diode can block and this diode can block. That means this switch can block positive voltage and negative voltage. In a power electronic converter with at least one control switch, there is a need to have a gate drive in order to turn on and or turn off a power switch. So the point is that we just concentrate on three different switches: thyristors, IGBTs, and MOSFET. So thyristor is a special switch. That means we can just turn on by applying gate signal, and MOSFET means that we can turn on and turn off, same as IGBT, when we apply gate signal and remove the gate signal. So the point is that in some applications we need galvanic isolation. That means when we have a controller, basically what we get from the controller is a pulse pattern with respect to this ground. And in some applications we have a switch placed in this circuit and the emitter is connected to the ground. So that means if the voltage level is enough, we may turn on and turn off the switch without any problem, because the point is that to turn on and off a switch like MOSFET or IGBT, we need to provide positive voltage with respect to emitter. And because emitter is connected to the ground and because we have already positive voltage, that means in this configuration we are able to turn on and off the switch. But in some applications we may need more voltage level. For example, if the voltage we get from the controller is 5 volt and if we need, for example, 15 volt, so in this case we need to have a gate drive in order to increase the voltage level from 5 to 15. That means keeping the same voltage waveform but increasing the voltage level. In some other power converters in which we have some power switches that emitter is not connected to the ground, so in this case if we have gate signal with respect to this ground, so that's why we cannot connect it directly to gate terminal, because we need to provide enough voltage with respect to emitter. So that's why we need to have galvanic isolation, for example in this case using a transformer, pulse transformer, and then here we have same gate signal even at different voltage level, but because these terminals are floating, then we can connect this terminal into the emitter and this terminal into the gate. So that means whatever I have here from the controller, I can generate the same signal, same voltage waveform, even at different voltage level, and then we can connect it to this transistor. So in this case it's possible to have galvanic isolation, and it's possible to turn on and off different power switches which are connected in different cases, which has different emitter voltage, which has different gate voltage, and in this case we can see that emitter is not connected to the ground, so we are able to turn on and off the switches. To have galvanic isolation there are different configurations. For example, one of the method is using optocoupler. So when we have a controller, when we have a voltage from the controller, then we can apply to this diode, and then we turn on and turn off the diode, and at the same time in the secondary side we have a transistor can be turned on and turned off. So this part are isolated, and then we can get the signal across the output here, and this voltage is totally isolated from the input side. Then we can apply this one to the gate and this one to the emitter. A drawback is that this one needs a separate power supply. The second method is using pulse transformer. So basically using pulse transformer, what's happened, we can provide again gate signal. When we have a controller, we get the pulse pattern from that one, and we can get the gate signal from here That means using that one, this type of galvanic isolation, we can connect this terminal to the gate and this terminal to the emitter. But again, a drawback is that the duty cycle, that means the time that the switch is turned on and the time that the switch is turned off, should be controlled. So the maximum duty cycle that the system can handle is between 35 and 65%. And also another drawback is that the leakage inductance, because this transformer cannot be an ideal transformer, there is a leakage inductance may affect the switching speed. Now let's look at power switches in different applications. For example, if we need to have a high power supply, or we need DC drive system, high power DC drive system, so we can use AC DC converter based on Thyristor. So in this case, we can only use Thyristor in this application. So this is the switch that can be used in this type of application. But if we need to have, for example, high quality power supply or a DC motor drive for servo drive applications, then we need high quality DC-DC converter. And if the input source is AC, first of all we need to rectify the voltage. So in this case we need the diode for this configuration to get DC voltage, and then through this DC-DC converter we can get regulated voltage. And in this DC-DC converter, basically we can use MOSFET with diodes, fast diodes. And in some applications, if we need to operate at high voltage, high frequency, then we can also use IGBTs. Or if we need to get AC voltage, that means if we have to generate AC voltage, in this case we need to use DC-AC converter. So for DC-AC converter, basically we need to have power switches like IGBT, and in some applications at operating at low voltage we may have MOSFET. But because in most of AC drive system we have inductive and resistive load, so that's why we need to actually handle bidirectional current. So in this case we need to have diodes as well. So same scenario happens if we need to get the DC voltage from DC or AC voltage from DC. That means if the input is DC, then we need to boost the voltage in some applications. Again, we need to have DC-DC converter. That means we need to have this type of switches for these applications. Welcome to Power Electronics Education Electronic Book, Tutorial 2, Power Switches. This tutorial is presented by Dr. Firuz Zare. So in this example, we have to find the conduction and switching loss. This is the voltage waveform, and this is the current through the switch. So basically when the switch is off, assuming that the leakage current to the switch is 0, so that's why there is not any conduction loss associated with turn-off time. And this is a transient, that means the switch is getting off, and this is the transient when the switch is getting on. So the voltage drop across the switch is V on, which is basically 2 volts, and the current through the switch is 10 amps. So when the switch is off, the voltage across the switch is 500 volts. So we can find the conduction loss when the switch is on, and we can find the switching loss when the switch is getting on and off. So let's start with conduction loss. To find the conduction loss, we need to basically multiply the voltage across the switch with the current through the switch, and over the time, which is basically this time. So if one cycle is 100 microsecond, so if this point is 50 microsecond, so this point is 50 microsecond plus t on, so t on is 1 microsecond. That means this time is 51 microsecond. So the time that the switch is in on state is 100 minus 51 microsecond over Ts, which is 100 microsecond. So in this case, 2 times of 10 amps times of 49 over 100 is the conduction loss, which is basically 98 times of 10 over 100, or the conduction loss in this case is 9.8 watt. And then we can look at the switching loss. Basically, to find the switching loss, either for on or off state switching states, we need to calculate this area associated with switching loss. So I think the best step to find that one is to draw the power waveform. So if we multiply current and voltage, then we get this power waveform. This peak is V off times of I on, because this is the I on and this voltage is V off. So we can find the peak of this waveform. So similar for this case, which is basically V off times of I on. So the point is that this cycle, this switching time is 1 microsecond, same as 10 on time, 1 microsecond. So this power, this peak value is 500 times of 10, that means 5000 watt, same as here. So in order to find the average, we need to find this area, which is basically this height times of this side over 2. So that means for 10 on loss, we have 500 times of 1 microsecond divided by 2. That's the energy divided by switching cycle, which is 100 microsecond. So in this case, we have 50 over 2 or 25 watt. So now we can find the switching loss for off state, which is basically same as switching loss for on state, because this switching time is same as this switching time. So in this case, the switching loss for 10 off time is 25 watt. So finally we can say that the total switching loss, which is switching loss for off state plus switching loss for on state is 25 plus 25 is 50 watts, and peak conduction was 9.8 watts. So the total loss for a switch in this case is 59.8 watts. So in this question we have a DC voltage which is basically 200 volts plus minus 10%, and when we apply gate signal we turn on this thyristor, but the point is that when we remove the gate signal we have to find the current through the thyristor, and if the current is less than latching current, that means the thyristor will be turned off. So in order to find the best signal for this thyristor, we have to be sure that at the end of this gate signal the current through the thyristor is more than 50 milliamp. So now let's look at the worst case. Let's look at the input voltage. When input voltage is with this tolerance plus minus 10%, that means minimum and maximum input voltage are 220 volts and 180 volts. So in worst case means that we have minimum voltage across the circuit, and in this case that can increase the current. That means compared to this voltage level we may need longer time to be able to increase the current through the inductor. Let's look at the inductor. Basically the minimum and maximum values for this inductor is 0.95 millihenry and 1.05 millihenry. So we have to consider this value for worst case, because basically large inductor requires more time to increase the current in a particular level. So in this case the input voltage is 180 volts and inductance value is 1.05 millihenry. So now we can find the minimum pulse width to be able to turn it on and keep it on when we remove the gate signal. So let's look at the case when the thyristor is in on state. That means the input voltage, which is DC, appears across the inductor. So the voltage across the inductor, VL, equals to Vin. So Vin is 180 equals to VL, which is L di dt, or L is 1.05 millihenry times of delta I over delta T. So in this case delta T equals to 1.05 times of 10 minus 3 over 180 times of delta I. So basically the latching current should be considered in this equation, because when we apply gate signal and turn on the thyristor, then the current through the thyristor and through the inductor is increased, So basically this is delta I, if this is current waveform. So we have to be sure that at the end of this pulse, the current reach to the latching current. So if latching current is 50 milliamps, then we should consider in this equation. So that means delta T equals to 1.05 over 180 times of 10 minus 3 times of 50 milliamps, which is 10 minus 3, or that equals to 1.05 times of 50 over 180 times of 10 minus 6, or we can simplify that one, which is 5.25 over 18 microsecond. So this is the minimum pulse width to guarantee that the thyristor current or inductor current reach to 50 milliamps. So in this case, the pulse width of the gate signal should be greater than that value, which is 5.25 over 18 microsecond. So this is pulse width for a gate signal.